Hello, this is David Kyle Johnson, Associate Professor of Philosophy at King's College in Pennsylvania. And I would like to present to you a presentation I gave at the Williamsport Regional Medical Center for their continuing medical education program on June 17th, 2016. I'm actually recording this before I actually give the talk as a kind of practice for the talk. But it's also the case that this will likely be a little bit longer than the talk that I gave that day, simply because time permitting, I had to squeeze kind of squeeze a couple things in, or actually edit a couple things out to make sure that the talk went the correct time. So I was asked to give this talk basically because the revelation that diagnosis actually is abduction was thought by some people at the continuing medical education program there at the Williamsport Regional Medical Center as a really good way to avoid diagnostic error. And so basically that's what I'm going to do here, is try to ultimately explain diagnosis as abduction with the purpose of teaching how, or at least improving one's skills for avoiding diagnostic error. Okay, so diagnostic error is a huge problem in the medical industry, and clearly the solution to this problem is going to be multifaceted. It's not going to be just doing what I'm suggesting today, which is enhancing critical thinking skills that are relevant to the diagnostic process, but you need better reporting. You need to have more people reporting when diagnostic errors are made so you can learn from your mistakes. You need to be holding people accountable for diagnostic errors. There'll be kind of a balance between holding people accountable but also encouraging people to report them when they happen, right? So you need better records kept of the errors and that kind of stuff. It's a very huge problem with a multifaceted solution. And the problem will never be completely solved. The goal, there should, you can have kind of an idealistic goal to eliminate, a diagnostic error, but it's not realistic. It's never going to happen because diagnosis is an inductive form of reasoning. And as a result, it can never be perfect. The conclusion will never be guaranteed. All right. Now, that may be confusing to some people because they have a certain understanding of what inductive reasoning is, and it may not be quite clear why inductive reasoning can't be 100% reliable. Well, so it's important here early on to make a distinction between classic and modern understandings of the difference between deduction and induction. Okay, so in the classic understanding of the difference, induction is reasoning from the specific to the general. For example, you would observe events to try to figure out what the laws of physics are. Right? You look at a bunch of events, see what they have in common, then you infer a law from that. So, for example, this rock fell when dropped, so do these other 30 rocks, thus all rocks fall from when dropped, right? From the specific to the general, right? And then it's thought that the deduction is the opposite, is general to the specific. For example, you could use the laws to predict an event, right? So all rocks fall when dropped. I drop this rock, therefore this rock will drop, right? So, or I guess more specifically speaking, it should be this rock is all rocks fall when dropped. Therefore, this rock will fall, I guess is what the conclusion there should be. Sorry about that. But the modern understanding of deduction and induction is different. In the modern understanding, deductive arguments are arguments whose premises are supposed to guarantee their conclusion. If the premises were true and the argument actually is deductive and it's valid, then the conclusion would be guaranteed. Inductive arguments are arguments whose premises are supposed to merely support their conclusion, but not necessarily guarantee it. So you could have a really strong inductive argument, all the premises could be 100% true, and the conclusion could still be false. That's possible with an inductive argument. That's impossible with deduction. In deduction, if the premises are all true, the argument's valid, the conclusion has to be true. There's no escaping it. In an inductive argument, you could have a strong argument, all true premises, but the conclusion could still be false because the premises merely support the conclusion. They don't guarantee it. All right, and that's the difference in the modern understanding between deduction and induction. Deductive arguments guarantee their conclusion. Inductive arguments do not. They merely support their conclusion. The modern definition, the modern understanding or distinction between deduction and induction is superior because it encompasses all arguments. You can classify all arguments as either inductive or deductive. on the modern definition. You can't do that with the classic definition. The classic definition, you'll have some arguments you don't know how to classify them. For example, all dogs are mammals, all mammals are animals, therefore all dogs are animals. That's not general to specific or specific to general. The classic account can account for this argument. It can't classify it. But it clearly is deductive in the modern sense. So the reason that this is important to realize, and the way it relates to diagnosis, is that all science, including diagnostics, is inductive. Thus, no diagnostic process can ever be foolproof. It's always possible for the premises of a diagnosis to be true, and for it to be a good diagnosis, a solid diagnosis, and yet the conclusion still turns out to be wrong. Right? For example, no matter how good your diagnosis is, it's always possible for it to be some new unknown disease that has the same symptoms as the one that you think it is. That's possible, not likely, but that is possible, and so it can never be guaranteed. But despite the fact that it's an insoluble problem in that it can never be eliminated 100%, diagnostics can be improved. You can reduce the instances of misdiagnosis. Right? And one key in this clearly is to improve the relevant critical thinking skills. I found these very helpful images here on the right showing how to improve critical thinking skills. Right? Don't sit back on your couch, but instead lean over a desk. But there's one big problem. And we saw this in the reading that I assigned, or I asked attendees at this conference to read before coming to the talk. There's no single definite or good definition or description of diagnostic reasoning, right? The reading that we read defined 3 different diagnostic procedures called System 1, System 2, and Bayes. We'll talk about those 3 a little bit later, right? So we have like 3 possibilities here, but not one that describes all diagnostics, right? So if there's not a single or even good definition of the diagnostic process, well, then what skills do you sharpen? Right? If there's not a good definition of what the process is, it's hard to understand what skills you should sharpen, what skills that process involves, and thus what skills you should sharpen. So my goal here is to give a better description of the diagnostic reasoning and enhance your ability to avoid diagnostic error by teaching you how such reasoning works. So this will enhance and enable you to further enhance the relevant critical thinking skills. Okay, so ultimately my thesis is this. I am going to argue that diagnostics is a kind of reasoning called abduction, or inference to the best explanation, right? And abduction is a kind of inductive reasoning. That's why it'll never be guaranteed, right? Other kinds of induction include numerical induction or argument by analogy, right? Every diagnosis is the suggestion that some disease or condition is the best explanation for why the patient has the symptoms that he or she has. Right? That's basically the thesis, that every diagnosis is the suggestion that some disease is the best explanation for why the patient has the symptoms that he or she has. So, if you want to improve your ability to avoid diagnostic error, you should improve your ability to find the best explanation, to do abduction. So again, it's kind of a funny name when we say abduction. We're not talking about abductions, we're talking about abduction. Right? Abduction is actually the kind of reasoning that both House and Sherlock Holmes, House MD and Sherlock Holmes used, and we'll talk a little bit more about that later. Okay, so what is abduction? Abduction, again, is inference to the best explanation. We do abduction anytime we infer the best explanation from among alternatives, and we do it intuitively all the time in a variety of different ways and circumstances. For example, when we intuitively correct for misspellings, we're doing abduction. All right, so for example, take that sentence. What does it mean? Well, what's more likely? That I misspelled the word saw and meant someone saw what happened? Or that I'm commanding someone to sew an image of event? Someone sew what happened? Clearly the more likely interpretation, right, the better explanation, is that I misspelled the word saw. Right? We're doing abduction even when we simply correct for misspellings, right? And in fact, every misspelling and grammar error in this presentation will just be a subtle reminder of what abduction is. So what I think is that diagnosis is abduction, right? This definition, in fact, is so intuitive to me that I stated it without argument in the Big Questions of Philosophy. That's actually what actually generated my my invitation to give this lecture. But this doesn't seem to be something widely acknowledged in the medical literature. As we saw, we read something that talked about diagnosis, and it didn't mention abduction at all, right? I was only able to track down one source that expressly took this position, and it was a philosophy book on abduction, not a medical text, right? And not even they defended the claim that diagnosis is abduction. But I'm going to. That's my plan here. And to defend my definition of the diagnostic method, it will be necessary to first lay out a brief history of the philosophy of science and the scientific method. So, brief history. Science is an offshoot of philosophers. Science is a result of philosophers developing ways of discovering truths about the nature of the world. Right? Which philosophers? Philosophers like Aristotle and Aquinas. He was quite a looker. Galileo and Bacon. Francis Bacon. Hume, Mill, Whewell, Peirce. These are all people who developed methods, what we would now call scientific methods, for discovering ways that the world is, right? In fact, they were originally known as natural philosophers. Later, they were known as scientists. This is why philosophy sometimes has a bad reputation of being a discipline that makes no progress. Philosophy has made tons of progress. It's just that when it does, the progress it makes is so important, it ends up generating its own discipline and then gets another name, and no one realizes that philosophy was responsible for that advance. And so philosophy is stuck with all the questions that we haven't answered yet. As soon as it finds another answer, that spawns a new discipline, and philosophers don't get credit again, right? But philosophy is actually what has been the engine behind all the major developments in human intellectual progress. But there was a problem with identifying what the scientific method is. All of the natural philosophers described their methods differently and even disagreed with each other on how science should be done. Bacon criticized Aristotle, Whewell criticized Bacon, Mill criticized Whewell, and vice versa. Other philosophers tried to identify what the methods had in common, but they were unsuccessful. There was just too much variation among the natural philosophers to identify exactly what was going on. And the disagreements continue to today. There's no universal consensus on what the scientific method is. And attempts to identify the scientific method are sometimes called to be yesteryear's debate. Right? Ironically, the fact that there has been no agreement on what the scientific method is has not stopped textbook writers from articulating what they call, or what they see to be, the scientific method. Usually it goes something like this, and you've probably seen something like this in textbooks somewhere. You observe, you hypothesize, you deduce and predict based on that hypothesis, then you test to see if the deduction or prediction came out right, and then you accept or reject or revise the hypothesis depending on how the test turned out. All right? You've probably seen something like this in existing textbooks. But philosophers of science would all agree that this is incomplete and inaccurate. This does not actually describe the scientific method as it occurs in the real world. For one thing, observation is theory-laden. It must have some kind of direction or it's endless. Right? If I just told you to observe, if I just gave you the command observe so we can do some science, you could spend your entire lifetime in the room that you're in right now making observations about everything, and you'd never get any science done at all. You have to know what kinds of things to observe and what to ignore in order to even get the scientific process off the ground, right? And you know what's relevant and what's not because you already have theories in mind. You already have ideas and hypotheses in mind about what's relevant and what's not, and what problem you're trying to solve. That's what we mean by observation being theory-laden, right? And that was what I mean here by previous theories dictate what is relevant. And then how do we decide between revising and rejecting a hypothesis? So there's this great example in the history of science about the discovery of Neptune. We were using Newton to predict the orbit of the planets, and it always got it right except for when it was trying to predict Uranus. And occasionally Uranus would not be quite where we thought it should be according to Newton's laws, right? So what are we going to do here? Are we going to reject Newton's laws because it's getting the prediction wrong? Or are we going to somehow try to save Newton's laws by some kind of excuse or other hypothesis, right? And so what we actually did at the time was like, well, maybe there's another planet out there that's pulling Mercury's orbit off a little bit, and that's why it's not where we would predict. And so we did the calculations where such a planet would be and looked, and lo and behold, there was the planet that we eventually called Neptune, right? And so there's nothing here to try to let us know whether we should reject the hypothesis if it doesn't accurately predict what if it doesn't give us an accurate prediction, or if we should revise it, right? There's nothing in this process that tells us that. And what about replication? How many successful tests are necessary before you can accept the hypothesis, right? There's nothing in this textbook articulation that tells us that. What about rules of experimental design and guarding against mistakes in reasoning, right? There's all of these there's specific way. It takes an entire class to teach people how to, probably more than that, to really tell people how to set up an experiment correctly to guard against all the different ways that our reasoning and perception can lead us astray. And we also want to guard against fallacious reasoning when we're looking at evidence. There's nothing in this textbook scientific method that tells us how to do that or even includes those steps, but clearly that's part of the scientific process, right? Notice example that an anecdote would fit this, but is not science, right? So in other words, I could do something like, hey, I'm sick. Here's a pill I found on the ground. I think it will make me better. Let's see if it does. I'll take it and see if I get better. Oh, I took it. Now I'm better. The pill must have worked, right? That fits this observe, hypothesize, deduce, predict, test, and accept or reject. It fits this model, but clearly that's not science. Certainly not good science, right? And so clearly the textbook articulation is inaccurate. And a lot of astronomy doesn't fit this model, but clearly it's science. Like if we try to figure out the content of distant stars by looking at the wavelengths of light, like breaking apart the light that they put off and seeing the colors of light that are in the light spectrum it has, that tells us what the distant star is made of, but that doesn't follow this textbook scientific method, right? And then there's the Grue problem. The Grue problem cannot be solved it cannot be accounted for by this textbook scientific method, right? So the Grue problem is this. Being blue obviously is the property of something being blue. The property of being Grue is the property of being blue to a point and then turning green. So take this object that's on the screen here, this dot, right? There are two hypotheses that can describe what color the dot is. It could be blue, or it could be some shade of Grue. So we'll consider these two hypotheses. It could be some shade of Grue. Like it's Grue, it's blue up until 5 seconds from now, and then it will turn green. Watch it. Okay, it's not that shade of Grue, but maybe it's some other shade of Grue where it turns green at a later time, right? And no matter how long we observe it, we could always think, well, maybe it's some other shade of Grue. How could we ever know or even gather evidence that the dot isn't some shade of Grue? We could never do it through that textbook method on the last slide, right? The observe, hypothesize, deduce, predict, test, and accept, reject, revise hypothesis method. That will never tell us whether or not the dot is Grue, because no matter how many times we test it, it could always be some other shade of Grue, right? Now, this is a kind of funny problem. How can we know that the dot is not Grue? Well, here's the point. We know that the dot is not Grue. We know that that dot is blue. Indeed, we know that the Grue hypothesis is not even really scientific. But we can't establish this through that textbook scientific process mentioned on the previous slide. And so there's something wrong with that textbook articulation of the scientific process. Now, we might say that the Grue hypothesis is non-falsifiable, right? Because you can never falsify it no matter how long it stays blue. You could always say it's some other shade of Grue. But is being falsifiable sufficient, or is it necessary to be scientific? Does that really describe the entire scientific process? So very quickly, just a little bit about falsification. Some suggest that being falsifiable is necessary for a hypothesis to be scientific. This makes some scientists try to reduce all of science to testing hypotheses. I have this picture of Marx up here because this basically came about in response to people like Marx and other similar theories like Freudian psychology that were unfalsifiable, that basically they were structured in such a way that no matter what evidence came in, you could make that evidence fit into the theory. And so they could never get a prediction wrong because you always kind of finagle things so they got the predictions right. And so, for an example, for Marx, right? Basically, any Marxist society that didn't go right, you could just say, well, it's not a true Marxist society. You're not really implementing the ideas that not really implementing the ideas that I'm articulating, right? Or for Freudian psychology, you could always say that the motivation was unconsciously in line with Freudian, what Freud suggested, or something like that. Now, the problem with saying that falsification is required for something to be scientific is that, for one, many aspects of science aren't done in a lab or through tests. It's not always falsifiable in that classic way. I'd say string theory is science, but it's not falsifiable, right? It's theoretical science, but it's still science, even though it's not falsifiable. And sometimes it is acceptable to protect the theory from falsification against anomalies with an excuse if the theory is well established in the first place and the excuse is at least potentially falsifiable. So, for example, initially, evolution through natural selection couldn't explain why there were altruistic individuals in the animal kingdom, including humans, right? But that theory is so well established that it's okay to try to tweak the theory a little bit so they can account for this new information. This is how altruism led to theories about group selection. This is in fact how much scientific progress is made when the theory doesn't get the predictions exactly right. You don't reject it, you go back and slightly revise the theory to make it align with the predictions and thus improve the theory, right? Now eventually it needs to be rejected if it gets enough of the predictions wrong, right? But again, this is the falsification, neither the textbook method nor the falsification here tells us exactly how to do that, when we should reject it or when we should revise it. And notice that we can still distinguish scientifically between theories, even if they cannot be differentiated through testing, even if one of the other ones isn't falsifiable. A great example of this is with the geo versus heliocentric view of the universe, right? So if we were trying to figure out which view was correct, is the Earth the center of the solar system or the universe, as they would have talked about it back in the day, or is the sun the center? Right? Well, it turns out that if we were actually going to model what things would look like if the sun was the center or the Earth was the center, this is not what they would look like. This is actually what they would look like. Right? If the Earth, on the left here, if the Earth was actually in the center of everything, the orbits of the planets would actually look a lot more like that. And that's because if you trace what the planets do every night, occasionally they'll move from left to right, I believe, but occasionally so they usually move from left to right, but occasionally they'll double back on themselves and move right to left. And then they'll move left to right again, and then right to left for a little while. And it looks like they're kind of doing loops in the sky, as it were. Right? And so if the geocentric model is going to accurately predict where the planets are, it's going to have to look like this. But you really can make a geocentric model, that does actually get the predictions right. You could use it to predict where all the planets will be every night in the night sky, right? And it will predict it just as well as the heliocentric model, right? That has the sun at the center and all the planets orbiting around it, and the moon, of course, orbiting around the Earth, right? So, how could you prove one right or the other over the other, right? If falsification is all there is to science, there's no way that you could possibly prove one over the other, right? Because they make the same predictions. Now, that's not exactly correct, because they actually do make different predictions when it comes to parallax. If the Earth is orbiting the sun, there are certain stars that should look slightly different in the night sky at different times of the year, right? So on January 1st, the white star here should appear to be on the right, and then on April 1st, it should appear to be on the left, right? But here's the issue, though. I mean, here's the deal. Here's why I point this out. It turns out that back when we were actually trying to decide between the geocentric and heliocentric views of the universe, we weren't actually able to observe parallax. Our telescopes basically weren't good enough to be able to determine or see the stars, see this kind of difference in the stars during different times of the year. Right? We actually couldn't observe parallax. We have observed parallax now, and so we know that the Earth is orbiting around the sun, through that, right? But here's the thing. Here's why I point this out. We accepted the heliocentric model and rejected the geocentric model before we could actually observe parallax. We did it even though they made exactly the same predictions, right? So how are we able to do that? How are we able to know that the heliocentric was the better model or was the true model versus the geocentric if they made the exact same predictions, if there was no observable way to distinguish the two hypotheses, right? Clearly falsifiability. So in other words, they were equally, like they made all the same predictions, they were equally falsifiable, non-falsifiable. They made the same predictions. There must be some other criteria by which we can gauge the two theories to figure out which one is the best one. And as we shall see, basically what happened is we realized that the one on the right, the heliocentric model, was simpler. And so simplicity is another criteria by which we judge scientific reasoning. And that's because it's a part of the scientific method as abduction. So in other words, my solution to this problem that accounts for what the scientific method actually is to suggest that the scientific method is abduction or inference of the best explanation. I think it is the most accurate, and at the least, it is at least the most helpful understanding of the scientific method. I'm inspired to accept this thesis by Kuhn and Schick. I found my thesis about the scientific method defended by McMullen in 1992. He basically defends it through an historical argument showing how all the major historical figures in science were using some version of abduction. So what Kuhn tells us about why the scientific method is abduction, or why I think what Kuhn tells us suggests that science is abduction, is that he shows us that science is done within a paradigm or a meta-theory that informs the puzzles and testing methods that people are doing as they're doing science. And it discovers answers to puzzles by weighing competing explanations according to criteria. He says that paradigm shifts occur when anomalies mount up and we realize that a different new meta-theory is a better explanation than the previous one. In other words, you have this paradigm, it informs what you test, but sometimes it can't explain everything. Usually those things are kind of excusable away because the meta-theory is so well established. But if anomalies and things that the meta-theory can't account for keep piling up, and then a new theory comes along that can account for all the old data that the old theory did, plus it can account for these new anomalies, well, eventually that new meta-theory becomes accepted because it's a better explanation of what we observe than the previous one. Interestingly, these kind of paradigm shifts usually happen on a group level because of curmudgeons, because basically even scientists will get kind of wedded in their ways basically and won't give up their old favorite theories even in light of new evidence. This happened with plate tectonics, where Wegener and I believe it was Chamberlain, although it could be wrong, Chamberlain disagreed with Wegener. I know that Chamberlain disagreed with Wegener, but I think Chamberlain was one of these scientists, these old, one of these old school scientists that refused to accept plate tectonics even to his dying day. And it was like, his dying day was like in the 1980s or something like that, right? He went on believing for his entire life that plate tectonics was wrong, despite the overwhelming evidence. He just didn't go with the shift. But the paradigm shift did occur in the general scientific community, and that's why plate tectonics is accepted today. What Schick suggests is, so again, Kuhn suggests that science weighs, we try to answer puzzles by weighing competing explanations according to criteria and accept new meta-theories even whenever they are the better explanation according to these criteria. Schick tells us what those criteria are. Their testability. Does the hypothesis make novel predictions? It can't predict what we already know and actually be testable. Fruitful. Does it get those novel predictions right? Keep in mind that this is not everything. This is not the only thing that a hypothesis needs to do to be scientific. Getting those predictions right is only one of 5 criteria, right? Scope. How much does it explain? Does it unify our knowledge? Or does it invoke the inexplicable and or raise unanswerable questions? If it does, then it doesn't have wide scope. Simplicity or parsimony. How many assumptions or entities does the theory or hypothesis require? The more it does, the less simple it is. And don't confuse simplicity with easy to understand. Something can be complicated to understand, but could be simple or parsimonious because it doesn't require a lot of extra entities for it to work. And then conservatism, how well does it align with what we already know? Again, note that this is only one of 5 criteria. A non-conservative hypothesis can prove itself worthy by basically being testable, fruitful, having wide scope, and being simple, right? So if conservatism was the only criteria by which we judged a hypothesis, we could never come to learn that we were wrong. We could never update our knowledge, because if it doesn't align with what we already know, we would just be rejecting it, right? If it doesn't align with what you already know, that is a kind of a red flag. It's probably a good indication that it's probably false. But maybe what we already know is wrong. Maybe we don't really know what we think we already know, right? Maybe what we think is true is wrong, and this new theory is right. That new theory can prove itself by, even though it's not conservative, showing itself to be testable, fruitful, wide-scoping, and simple. Great example of a paradigm shift was our shift from Newtonian mechanics to Einsteinian relativity. Initially, Newton and Einstein made all the same predictions, so they were equally fruitful. They were both testable, but they made the same predictions, and so they were equally fruitful. Einstein developed relativity given the established knowledge, and so it did make all the same predictions about where the planets would be, et cetera, et cetera. Relativity was supposedly simpler, no force or gravity, but Newton was still accepted because it was more conservative. It was the established belief. I'm actually not convinced that relativity is simpler than Newton, because space-time, I think, is an entity like the ether, but that's a whole other issue. But relativity became more fruitful, however, when it correctly predicted that light bends around massive objects, and Newton did not correctly predict how light bends around massive objects. Now, there were still stragglers at the time because of curmudgeons. They would not give up on the old Newtonian theory. They had just grown up with it, and they weren't willing to give it up. But once it became more fruitful, and then it started to have more scope, the shift became inevitable. Without even intending to, Einstein's theory of relativity perfectly explained the perihelion of Mercury, this really weird orbit of Mercury that you see on the bottom right here, that Newton had no way to explain. Einstein could explain time dilation and a few other things, right? Once its explanatory power became clear, it was more fruitful because it was getting the predictions right about light bending and other things right more than Newton. The paradigm shift was inevitable, and eventually we rejected Newton's theory. It still gets some predictions right, but we rejected it as a meta theory and came to accept relativity. Now, today, to deny relativity is non-conservative. It's the established belief. I think this is the most useful definition of science because it's very useful for identifying pseudoscience. For more details on this, you can see Pigliucci 2010. For example, homeopathy. The criteria of abduction clearly demonstrate why homeopathy is a pseudoscience and not a science, right? So, what is homeopathy? You probably know it's a suggestion that diluting a substance will reverse and enhance its effects. If you have a substance that causes disease X, then dilute it, and that will cure disease X. Right? This is testable. This is a testable hypothesis. It predicts that homeopathic remedies will do better than placebos in double-blinded trials. But it is not a fruitful hypothesis because they don't do any better than placebos in such trials. It doesn't have wide scope. It can't explain how it supposedly works, other than saying the water remembers the essence of substances, the substances it once contained. But these raise unanswerable questions. How does the water remember? What is a substance essence? And so it has no scope because it raises those unanswerable questions. It's also not simple because it requires water memory and substance essences for the hypothesis to be true. So it's got extra assumptions in it. And it's also not conservative because it conflicts with what we know. What do we know? Diluting substances does not reverse and enhance their effects. It weakens them, right? So it fails 4 of the 5 criteria. We know it's not scientific for that reason because it fails that criteria. So, if science is abduction, how do we do abduction? Well, Schick's got a great abductive method that he calls the search method. And here's how it goes. You state a hypothesis, a possible explanation as precisely as possible. This is often a non-scientific process that is based on assumptions and is more akin to artistic creation. Although in medicine, you do have a bank of choices, like a kind of like in other words, you have identified conditions and diseases, and you can choose from basically those conditions as possible hypotheses. Then you evaluate the evidence for the hypothesis. Is there invalid logic that supports the hypothesis? Logical fallacies? Are there just anecdotes? Just observations? Are the observations reliable? The limits of senses and memory and intuitive reasoning all have to be taken into account for. Are there authorities cited? Are they relevant authorities? Are there studies? Are these good studies? Are they double-blinded studies? Do they have flaws? Right? You ask all those kind of questions when you're evaluating the evidence. Then you evaluate alternatives. You state and evaluate the evidence for at least one alternative hypothesis. This is important because if you only do step one, you're really not getting anywhere, because anyone can gather evidence for any hypothesis, right? If you want to believe that Santa's real, I can give you evidence. There's a bunch of kids who believe that it's real, and there's a bunch of presents that they can't explain how they got there other than Santa giving them, right? Those are both pieces of evidence for Santa. If you don't consider evidence against Santa, you might actually fool yourself into thinking that Santa is real, right? If you want to know whether you are right, you shouldn't just try to prove yourself right. You should try to prove yourself wrong. Because if you try to prove yourself right and succeed, well, surprise, surprise, you tried to prove yourself right. If you tried to prove yourself wrong but didn't succeed, that's a pretty good indication that you're right. Right? So you need to state alternative hypotheses and competing hypotheses with your initial hypothesis. And then so you state and evaluate the evidence for that alternative hypothesis, and then you rate according to criteria of adequacy each hypothesis. You look and see how do they do on testability, fruitfulness, scope, simplicity, and conservatism. The one that scores the highest is most likely, right? So clear example on this is you can apply the search method to seeing which one is more scientific, evolution or creationism, right? I actually have another video that goes on for an hour about this, so I'm going to leave this here, let you read the slide for yourself just to save a little time. But if you're really interested on why evolution is clearly good science and creationism is not, I have another lecture on that already up on YouTube. Search is the best method, I think, because for one thing, it's very usable. It's flexible enough to be used in all situations, even outside of science. That's what Schick does in his book, How to Think About Weird Things. He uses it everywhere, all over the world, especially about how to think about weird things. And it's very, very teachable. You can show how the step-by-step process works, show all, and show all the criteria that are involved. And it's very, very teachable. And it's broad enough to encompass, I think, all major scientific approaches. I'm sure there are some exceptions. There might be some retrofitting to make them all fit, but generally it's broad enough to encompass all, or if not most, if not all major approaches. And it includes all the major facets of classic scientific reasoning. It includes falsifiability. It also explains why falsifiability is not necessary, so it includes string theory as being scientific. So that's why I think the search method is the best method of abduction and also the best articulation of what science is. Search also includes or accounts for what other descriptions do not, right? For example, the textbook description has no place to look for mistakes in reasoning. Search does. It acknowledges that observation is theory-laden because the problem is previously motivated. It's consistent with paradigm shifts and can survive them, right? In other words, you can use abduction, and abduction can actually lead to a paradigm shift, but when you make that paradigm shift, you don't abandon abduction. You're still using abduction. You're just updating what the best explanation actually is. And so the scientific method remains constant even through paradigm shifts in science. And it also explains how we can differentiate between theories without being able to test them. So for example, we can understand why we accepted the heliocentric over the geocentric model because it was simpler, because it was the better explanation, because it was the simpler explanation, even before the two theories could be differentiated by fruitfulness, right? By being able to make successful predictions, or one being able to make a successful prediction when the other one didn't. We could still tell which one was better because one was simpler. It also solves the Grue problem. How do we know that the dot is blue and not Grue? Because the dot being blue is the better explanation. It's the simpler explanation. Thinking that it's going to magically change colors at some moment adds an extra assumption that the blue hypothesis doesn't include. So that's the better hypothesis. And once the blue hypothesis is just made more likely than the Grue hypothesis, because it's simpler, then we can say, well, is it Grue type number 1? Nope, it didn't change color then, and that will actually, like if we use Bayesian reasoning, which we'll talk about in a little bit, that actually makes the Grue hypothesis, every moment that it's not turning Grue, that it's not turning green and thus showing itself to be Grue, the probability that it is Grue drops dramatically once you assign your priors, thanks to abduction, thanks to the criteria of abduction, and you can actually show that it's more likely that the dot is blue than Grue. But you can only do that by using the criteria and to set the priors and then using Bayes' theorem. So, all of that, how does this apply to diagnostics? I think defining the diagnostic method has remained I think it has remained as problematic as finding the scientific method. But I think just like with the scientific method, the best description of the diagnostic method is abduction. Every diagnosis is what is thought to be the best explanation for the patient's symptoms. Why? Well, recall the 3 descriptions of the diagnostic process. There's system 1. This is the non-analytical, fast, and intuitive method. Basically, it's pattern recognition based on past experience. You see patients present with certain symptoms, and you kind of intuitively know what disease they have. This is more common with veteran doctors. Then there's system 2, the analytical, slow, and careful reasoning method. This is very common among newbies. The method as it's articulated in the text, you have Q acquisition or observation, you have a working diagnosis or hypothesis generation, you have Q interpretation, where you predict and test based on that hypothesis, and then you have hypothesis evaluation or revision based on how the test turned out. Again, this is more common in newbies. Do you notice anything familiar about System 2, but the method in System 2? It mirrors the inaccurate textbook scientific method. That's the same steps as that textbook scientific method. Observe, hypothesize, predict and test, and then revise according to how it turned out, right? And so it's going to have all the same problems that textbook articulation of the scientific method had. The third description was Bayesian reasoning. You identify prior probabilities and then update those probabilities based on new evidence. And Bayes is great. I'm not knocking Bayes at all. It's very helpful in avoiding mistakes in diagnostics based on false positives, right? So, for example, in the text, there's the example of the breast cancer example, right? So you have a situation where only 1 in 100 women at the age of 40, let's say, have breast cancer, and you have a breast cancer testing procedure that is 90% accurate, so 10% of the time it will give a false positive, right? And then you have somebody that's a woman that's 40, and then she has in a population of 100,000 or whatever it is, and she has a positive test. Her test comes back positive for breast cancer. What are the odds that she has breast cancer? Intuitively, we think, oh, well, it's 90% accurate, so the odds that she has breast cancer is 90%, right? Well, it turns out that's completely wrong. Before she went into the test, she only had a 1% chance of having breast cancer because that's how rare the breast cancer is in the population. The test comes back positive, but 10% of the time it is, well, I should say, how do you say this correctly? 10% of the time you get false. 10% of the people who don't have breast cancer, it will give them a false positive. Well, it turns out there's a lot more of those than there are people who have breast cancer end up getting the correct diagnosis, or the test comes out positive. So it turns out that getting a positive result on the breast cancer test in the situation, even though the test is 90% accurate, only raises the probability that the woman has breast cancer to, like, I think the number is like 8% or 7%. It's a very low percentage. a very unintuitive. You would think it's kind of unintuitive. You think it'd be a lot higher than that, but it actually doesn't raise the probability all that much because even though it's 90% accurate, given the low probability of breast cancer in the first place, it stays pretty low. Right? Bayesian reasoning helps you avoid those kinds of intuitive mistakes, thinking that it goes really high. A simple positive test makes the probability go really high when it doesn't. Right? But these three descriptions, again, System 1, System 2, and Bayesian reasoning, these three descriptions fall short as a description of the diagnostic process because, one, none are universal. That's why there's three, so none of them totally encapture the diagnostic process completely. System 2 has the same shortcomings as the textbook scientific method. How do we tell which observations are relevant? How do we decide between revising and rejecting? For example, does a negative test mean the disease is absent or that it's just presenting atypically? Right? So an example from my own life here, this is my dog Zorro. He has still since passed because he had a tumor in his nose. Well, when we first saw the bump appear, we took him to the vet. The vet did a blood test, and there was no elevated white cell count. It's either white blood cells or red blood cells that are more present whenever your body's fighting an infection like cancer, right? But he did the test, and those antibodies were not. The white blood cell count was not up, right? And so he's like, oh, well, then it's not cancer because his body's not fighting it, right? Well, it turned out he totally had cancer. That was a cancerous tumor in his nose, and it eventually killed him, right? It's just that he was presenting atypically. The cancer was presenting in him atypically, right? So you get a negative test, but does that mean the disease is absent, or does that mean that it's presenting atypically, right? The System 2 method gives you no way of telling whether or not which one of those is the case, right? And so clearly it is inaccurate, inadequate in that way. And what about guarding mistakes in reasoning, anchoring and effective bias, availability bias, premature closure? These are all fallacies that you want to avoid in diagnostics, but nowhere in that diagnostic method, in the System 2 diagnostic method, are those things guarded against, right? And then with Bayes is very useful, but it's not always applicable. There's not enough information. And then you have the problem of what do you do if the two hypotheses predict the same evidence? Using Bayes will tell you that they're equally likely, but they may not be, right? Bayes can't solve the Grue problem. It can't always set, in other words, it can't always set the prior probabilities, right? But sometimes you need to do that in the diagnostic method, right? And so search is a much better description, I think, of the diagnostic process, right? So here's how it goes. Here's how you would apply search, or here's how search describes a diagnostic method. A patient presents with symptoms that demand an explanation, right? So you generate a hypothesis consistent with the symptoms and make testable predictions based on that hypothesis, right? There's the state the hypothesis step, right? You then evaluate the evidence for that hypothesis. Test results, you make sure no fallacious reasoning was involved in generating the hypothesis or in evaluating the evidence for the hypothesis, make sure the tests were done correctly, et cetera, et cetera. Once the test results are back in, you consider an alternative hypothesis that's also consistent with the evidence and makes predictions and consider the evidence for it. Now, if the test for the original hypothesis came back negative, you're going to need to consider an alternative hypothesis that's consistent with those negative test results, right? So you need a different hypothesis because more than likely your original hypothesis was wrong, unless the disease is presenting atypically, which is possible, right? But even if the test came back positive, right? So you have a hypothesis, you do a test for that hypothesis or that disease, it comes back positive, you should also consider an alternative hypothesis that's also consistent with that evidence, that would also generate a positive result from that test, right? Because the testing method, it will test for an indicator, usually not the disease itself, right? It doesn't directly test for the disease itself, like you're not like pulling the virus out or whatever, right? And so you generate an alternative hypothesis that's also consistent with those test results, and then you make predictions and consider evidence for it. So maybe do a second test or other methods of trying to figure out whether or not that hypothesis is true. Then you compare the two hypotheses to see not only which one got the predictions right? So maybe your second hypothesis failed the test that you put forward for it or whatever. But you also consider which one is most consistent with what we know, which one's most conservative, which one explains the most, has the widest scope, and which one is simplest, which one invokes the fewest entities. And notice that the more you repeat steps 4 and 5, the more alternative hypotheses you consider and discount or make sure that they're not right, the more sure you would be that your original diagnostic or whatever your diagnosis is correct. All right, so that's how it would go. I think search is a much better description of the diagnostic process than the standardly stated 3 methods for 3 reasons. First, all 3 methods involve some element of the search method. Second, B, real-world diagnostics include things that the 3 methods leave out but are encompassed by search. And C, when one of the methods leads you astray, it has neglected some aspect of the search method. So, by the way, this is Dr. Hibbert here on the left diagnosing Lisa with diagnosing bad babysitting as the cause of Bart's injuries. And then, of course, we have Dr. Nick Riviera here on the right. Obviously taking advantage of the fact that sometimes he has misdiagnoses. So again, why is the search method the best description of the diagnostic method? For 3 reasons. 1, all 3 methods involve elements of search. An effort to find the best explanation describes all 3. All 3 involve hypothesis generation. Right? System 1 recognizes that hypothesis generation isn't scientific. Observation is theory laden. Right? Has a lot to do with background evidence and what theories you already think are likely and that kind of stuff. System 2 and Bayes involve some evidence evaluation. System 1 can involve this, but doesn't always. System 2 and Bayes can include alternative hypotheses, just like the search method, but again, they don't always do this. Bayes aligns itself with existing knowledge. In other words, it favors conservative hypotheses like search does when it sets prior probabilities based on statistics. And like search, Bayes has a flexibility that allows for it to not be led astray by false positives and false negatives. Search avoids this because fruitfulness is not the only criterion. The second reason I think search is best is because search encompasses what the other theories of diagnosis that we considered don't encompass. They encompass things that real-world diagnostics include that the other ones don't. For example, it aligns what I think the scientific method really is, abduction. But it also accounts for criteria of adequacy, which are involved in diagnostics, but are nowhere encompassed in any one of the 3 other diagnostic methods that the reading that we read suggested. None of them weigh hypotheses according to the criteria of adequacy, but we do that in the real world when we do diagnostics. For example, simplicity. We all invoke simplicity. That's why we usually account for multiple symptoms with 1 disease instead of 2, because that's the simpler explanation, right? That's not included. That fact that we favor the more simple hypothesis is not included in any of the 3 methods that we discussed. This is actually like the 3rd episode of House MD, I think is called Occam's Razor, and that's the whole point of that episode, is that the best explanation for symptoms is usually 1 disease instead of 2. But what's great about the search method is that sometimes it does turn out to be 2 diseases. Sometimes people do have 2 diseases at once. If that is the case, however, doing the search method will eventually find that out. There's a corrective for this with the search method, right? So yes, simplicity says that we should favor the 1 disease hypothesis over the 2 disease hypothesis, everything else being equal. But if it turns out that the 2 disease hypothesis is more fruitful and has wider scope and is more conservative, then we should accept that hypothesis even though it's not the simplest, right? So the search method has a corrective in it that allows us to avoid that mistake as well, right? Scope or explanatory power, right? The methods that we discussed, the 3 methods, don't incorporate this at all, but clearly this is something that we use in real-world diagnostics. This is why demons did it. Is never considered a legit hypothesis. It invokes the unexplicable, and thus such an explanation would have no scope, right? New or an unknown disease is usually not considered a legit hypothesis as well because it raises more questions than it answers and thus has low scope. Again, if it turns out to be a new disease, the search method will eventually find that out, but that's because we have a corrective. We have other criteria to consider rather than just explanatory power, right? And scope can cause you to go back and reevaluate assumptions and observations. A diagnosis that can explain something that was once thought irrelevant has wide scope and is likely right, but that fact is not accounted for by any of the three hypotheses or any of the three diagnostic methods that we discussed. Then there's conservatism. We reject hypotheses and treatments that conflict with established knowledge, like alternative medicine and chronic Lyme disease and that kind of stuff. But again, that's not accounted for by any of the three methods. Diagnosing something because it's going around likely involves simplicity, scope, and conservatism. Search expressly includes guarding against fallacious reasoning, biases, anecdotes, misleading perceptions, etc., but none of the other three methods we've considered do. Right? So again, search encompasses what the others don't. And then the last reason that I think that the search method is a better description of abduction is because where the other methods shortchange abduction is where those methods lead you astray. So Bayesianism, for example. Bayesianism can fall short when it fails to compare more than one hypothesis, something that Bayes doesn't require, but the search method does. It can fall short when it does not incorporate the recognition of fallacies into either evidence evaluation or prior probabilities. Right? So, for example, availability bias may make you give a higher probability to a hypothesis or ignore a certain relevant evidence or something like that. Right? Bayes does not require you to factor in fallacies for evidence evaluation or prior probabilities, but the search hypothesis does. Right? And when you don't do that, that's when Bayes could lead you astray. Bayes would lead you astray if it gives you the wrong values to priors, but abduction can be used to set prior probabilities, right? So in other words, you can, before you even start doing Bayes, you can look at your hypotheses and set the priors by figuring out which one matches up to the criteria the best, right? And you can set your priors that way, and when Bayes fails to do that, when it fails to set the priors correctly, it can lead you astray, which it wouldn't do if it used abduction or the search method to set those priors. How does System 2, where does System 2 shortchange abduction and thus lead you astray? System 2 can lead one astray because it mostly is about fruitfulness. It's basically about prediction and testing, but it neglects how hypotheses are generated. It neglects being careful about fallacious reasoning like affect bias. And it also neglects how the other criteria, scope, simplicity, etc., factor in. As a result, you might neglect a relevant symptom, fail to consider a relevant correct hypothesis, consider an irrelevant wrong hypothesis, or draw the wrong conclusion about which is most likely, right? So all of these things, the hypothesis generation, recognizing hypotheses are generating, being careful about fallacious reasoning, considering the criteria, scope, simplicity, and stuff like that, those are all things that search requires you to do that System 2 does not require you to do, but when you don't do them, you can do all of these things wrong. You neglect a system, fail to consider relevant correct hypothesis, etc., or draw the wrong conclusion, right? System 1 can lead you astray when it shortchanges abduction, because basically it's a shortcut method that saves time but fails to give the needed attention to most search steps. This is why System 1 is most apt to fail. It concentrates most on hypothesis generation and may only give one hypothesis real consideration. This can lead to confirmation bias. It doesn't formally look for logical fallacies or misleading reasoning like search does, and it only gives it best intuitive recognition to the criteria of adequacy, whereas search gives explicit recognition to them. Right? And all three methods can lead to what Steve Novella calls house syndrome, which search by its nature avoids. House syndrome is what one suffers from when one operates under the assumption that the goal of diagnosis or diagnostics is to discover the condition that you have. And if that is not accomplished, if you don't discover the condition, then the process is considered a failure. But that should not be the goal. The goal should be right treatments, right? And making sure that especially bad conditions are treated properly. Right? If you don't discover the single one definite condition that a patient has, that's okay as long as they're getting the right treatment, especially if they're treating for their symptoms, and what they have is not some kind of deadly disease that you could have done something about had you discovered it. by entailing that multiple hypotheses can have equal likelihood, search can make one satisfied in eliminating the worst case scenarios and then merely treating symptoms without identifying a specific non-critical condition. Right? So what you can realize is that, look, you could have, you could have disease A or B, both of them present with these symptoms, both of them would, give a positive test in this result, in this particular condition. Neither of them are lethal. Both of them are things that will eventually go away. We can just treat your symptoms and you'll be fine. And it's okay if we don't ever figure out which one you actually really have, A or B, right? As long as we know it's not C, cancer, we're good, right? The other methods can lead to the house syndrome, where you think you have to identify the condition, but search does not. So what's the upshot to all of this? How do you avoid diagnostic error? You sharpen your abductive skills. Since that's what diagnostics is abduction. You can help avoid diagnostic error by sharpening your abductive skills. And how do we do that? Well, here's a start. You can recognize that you can fail to identify what is the best explanation or what is the best diagnosis for 5 reasons. And I'm borrowing this from Josephson from page 7. So 5 ways that you can mess up your abduction. You tried to explain something irrelevant, or you didn't try to explain something that was relevant. For example, you ignored a relevant symptom, or you didn't ignore a non-relevant one, right? Or you did not consider enough hypotheses. Your differential was not broad enough, and thus you failed to consider the true hypothesis. Or another way it can go wrong is you miscalculate how adequate an hypothesis was. For example, you underrated the right hypothesis or overrated the wrong one. For example, you didn't realize how rare a particular disease was, or you didn't realize that there was a recent outbreak of a disease in your area. So you miscalculated how adequate the hypothesis was. Or you did not evaluate the evidence for the hypothesis correctly. So you did or read the test wrong, or you failed to recognize some fallacious reasoning that was supporting the hypothesis. Or you miscalculated what the hypothesis could explain. You thought a hypothesis could explain what it couldn't, or didn't realize what it could explain. For example, you didn't realize that disease D presented with symptom S. So you didn't realize that symptom S was a indication of disease D. So if you're going to guard against misdiagnosis, you need to avoid those. You need to avoid these errors. How do you avoid these errors? Be aware that observation is theory-laden. Think twice before dismissing a symptom as irrelevant. You may be subject to availability error, confirmation bias. If you've already decided it's disease D, you may overlook a symptom. Keep in mind that hypothesis generation is not always scientific. It's up to you to consider the right hypothesis. So stay up to date so you will have in mind all the relevant hypotheses. Know your surroundings, how prevalent and likely diseases are in your area, and keep up to date on what we know, right? Judging a hypothesis as conservative, as aligning with what we think we know, is only worthwhile if your medical knowledge is actually up to date, if you're up to date with what we actually do know. Be careful performing and reading tests, and remind yourself often of common medical logical fallacies. And know your diseases and conditions. Know how they present, both typically and atypically. So, I believe diagnostic error can be reduced if you consider diagnostics to be an exercise in abduction and inference of the best explanation, and give the necessary attention to each step. This may seem time-consuming, but with a lot of practice, it can become second nature, where you basically just do abduction automatically whenever you are doing diagnostics. All right, so there you go. There's some of the sources I used. I actually need to add a reference to Steve Novella's piece where he mentions the house syndrome. But you can just Google Steve Novella and house syndrome, and you can find that source. All right, there you go. I hope that was helpful. Take care.